Okay, let's now continue our discussion of sequences and series by moving on to geometric sequences. Okay, so as before, clues are in the name here. So sequences, as we already know, means just a list of numbers. We're not adding them together, we're not multiplying, we're not doing anything to the numbers, we just have a list. Now last time we had arithmetic, which meant that the difference between each terms was a sum, or there was a difference between each terms. To get from one term to the next, we were adding or taking away something between them. For geometric, it means that we are multiplying each term by a number to get to the next term. So, for example, 2, 4, 8, 16. This is a geometric sequence. Sequence, once again, is just a list of numbers. I'm not doing anything with them. Geometric, because I am multiplying each number by 2 to get to the next one. So that's what a geometric sequence means. Now we need to know what is the general formula to be able to work out what is the third term of this sequence, or the 6th term, or the 8th term, or the 112th term. Well, let's derive it just like we did with the arithmetic one. So, what information am I going to need? Well, I'm going to need to know the first term, which once again, I will call A, same as arithmetic. And we're going to need to know what I am multiplying each term by. And this I will call R. My R's are a bit curly, sorry about that. So A, my first term, R, whatever I am multiplying each term by. So let's have a think. How do I get from the first term to the second term? Well, I multiply by R, right? And then how would I get to the next term? Well, I'd multiply by R again. What about to get to the fourth term? Well, to get to my fourth term, I'm going to start with my first term. I'm going to multiply by R once, multiply by R again, and then multiply by R one more time. So I am multiplying by R 3 times. AR cubed will get me my fourth term. If I want to get to my 5th term, I'm going to multiply by R once more, my 6th term once more, and so on. So we know that my general form is going to be AR to the power of something. Now, what is that something? Well, similarly to the arithmetic sequence, it is going to be n minus 1. As we've just seen, to get to the 4th term, I only need to multiply by R once, twice, 3 times. It's never n amount of times because I'm already starting on 1. I'm already starting on a term. So I only need to multiply that term by R 3 times, and AR to the minus 1 is the general term, is the general equation for a term in a geometric sequence. Okay, let's look at a really difficult example using this equation for the general term in a geometric sequence. So we're asked, what is the first term in this sequence that goes 3, 6, 12, 24 to exceed 1 million? So let's have a think and let's work through this. First of all, let's try and identify my letters. I've got an A, an R, and an N that I need to work with. What's my A? What's my first term? Well, that is 3. That's nice and easy. Same thing with my R. Well, each term I'm multiplying by 2. 3 times 2, 6 times 2 is 12, times 2 is 24. So I know that my A is 3 and my R is 2. Now, I am asked to find the first term where my sequence will reach 1 million or exceed 1 million. So, keywords exceed, I'm looking at something that's greater than. So I am asked to find the first term whereby AR to the n minus 1 is greater than 1 million. So How am I going to go about solving this? Well, it's going to involve some logs. So let me rewrite this equation using the information I have. So a is 3 times by r, which is 2, to the n minus 1 must be greater than a million. Now, how am I going to solve this? Well, I'm going to want to, first of all, divide both sides by my 3. And I'm actually just going to rub out some of this board to get some more room. So I've rubbed that out, I've redrawn it a bit, got rid of the question, hopefully you have that saved. And now let's go from here. I really should get a bigger whiteboard or just use the one at work, but that'd be too easy. So let's solve from here. Nice and easy, let's divide by 3. So I'm left with 2n minus 1 over here is greater than 1 million over 3. I'll keep it as a fraction just because I don't want to deal with recurring decimals and things like that. And now, what am I going to have to do to both sides? Well, I want to take log of base 2, right? 2 to the power of something is greater than something else. So I'm going to want to take logs of base 2 of both sides to pull this power out. Of 2 to the n minus 1 is greater than log of base 2 of 1 million over 3. I really need a bigger whiteboard. Wow. Now, my log of base 2 and my 2 will cancel. So I'm left with n minus 1 must be greater than log 2 of 1 million over 3, which, if I throw that right-hand side into my calculator, I get 18.34. So n must be greater than 19.34. Now, if n must be greater than 19.34, remember the question was, at what point do I exceed 1 million? So at n equals 19.34, the 19.34th term in the sequence, I'd technically be at 1 million, but we can't have a 19.34th, that's even how you say it, term of the sequence. It's going to have to be the 20th term of the sequence, will be the first time I get over 1 million.